So, you're usually given a reactant. Okay? Sometimes you're not, but you usually are. So one of the very first good steps would be, how is that reactive? Okay? So in this case, where is that material reactive? Okay. Bromine, sort of, and carbon. So I like that you've listed both of those. Okay. The bromine, however, not reactive. Okay. The only thing it is doing is taking the electrons away from the carbon, which means we end up with an electrophilic carbon. Okay. So when we look at that starting material, that's what we see, an electrophilic carbon, and that's it. Okay. You'll notice that I don't look at any of the carbons or hydrogens around that. Why not? They're not reactive. Okay. So again, what we're trying to do is go back to those basic definitions and try and classify. Start to see what you can use. Okay. If you look at the entire structure, you will get lost. Almost always in a synthesis question, you are asked for a product, or they give you a product and they want you to make that. Okay? That's probably the more common one. So do the same thing with the product. Where is your product reactive? And in the product, you'll typically find a lot more reactive sites. So where do we see reactive sites in our product? Okay. We've got an alkene, we've got that oxygen. There's no alpha hydrogens. Our alpha hydrogens are in reference to a carbonyl. Technically, there are alpha hydrogens here. They just don't react that way. Okay. Why do we look and identify our alkene and the oxygen? The oxygen is electronegative, which does what to the bonds? It makes those polarizable. Those could be bonds that I could make, okay, in the course of this reaction. The other thing I could do by looking at the alkene, that pi bond on the alkene is also a bond that I could make. It has some chemical reactivity. So what we're trying to do is to just identify what things are reactive. Okay? One of the next fun questions that can come out of this is identify constraints on your sources of carbon or reagents that you're allowed to use. You already have one constraint immediately out of the gate for every synthesis question. The only reagents you're allowed to use are the reagents that have been talked about up to that point in the semester. Okay? So don't be thinking going beyond that. Okay? If we're going to ask you a question, theoretically you should have seen all of those reagents already. Okay? And this quick question, is there any constraint put on you about anything else? The way this question is phrased. We can use anything we want. There's nothing in our direction saying you cannot use this reagent, okay, or you cannot use this source of carbons. So we don't have any extra constraints. Our major functional group changes. The next big thing, which we already started to work through, we've got an alkyl halide that becomes an alkene somehow, and also somehow becomes an ether. So we're looking at these big changes. How can we make these changes? And then potentially one of the last steps before we start moving into it is identify the carbon skeleton. So in our starting material, we have a carbon skeleton of 3 carbons. When we go to our product, we have a carbon skeleton of, except a couple answers on this. I would probably go with 2 sets of 3 carbons. Why not 6 carbons? The oxygen is breaking it. Okay, so we aren't forming any carbon-carbon bond. Which brings up our next aspect. In the course of this reaction, at no point do I need to attach carbons to carbons. Okay? So we're just looking for those pieces and kind of keeping them in the back of our head and saying, okay, what can we do with this? Okay? Similar process is set up with conversions. We know where we want to end. We know what we start with. What can we do? Right, and at least the way I teach conversions, our very first step after we've identified the beginning and the end, guess. What can you do to an alkyl halide? Why do you say elimination and not a substitution? Product has an alkene. That's just jump straight into it and attempt to run an elimination reaction. We'd end up with our double bond. How might we do that step of the reaction? What would we need to help that reaction occur? Not acid. Okay, it's identifying what other changes happened. Our other change is that we lost a hydrogen, which means adding a strong base would help us out. Okay, you'll notice I've still even used text. I'm not even specifying a reagent yet. Okay. I now have an alkene. So now what I might do is say, ooh, goody, I have a new problem. Where do I see that material show up in my product? The left side shows up in my product. That's kind of cool. The carbon at the end there would then equate to that carbon, right? We're just looking for our pieces. If we compare our starting material now, our new starting material, to our product, what's the issue at that carbon? I know it's a weird question. It's primary allylic, but it's primary allylic in both. In our product, what charge is that carbon? Two answers. Partially positive. That's the most important one. Why is it partially positive? The oxygen is sucking electrons away. When we look at that same carbon in our starting material, what charge is that carbon? Neutral. What does that mean? It's neutral, yep, same electronegativity around it. Can that carbon directly translate through? No. What has to happen to it? If we're saying those are one and the same carbon, what has to happen to that carbon? We have to remove a hydrogen. Okay. Actually, let's take that a further step. We have to actually lose electrons. So it's not just removing a proton. As you remove a proton, what charge does that carbon become? Negative. That is the absolute opposite of what we want. We want it to become positive. Okay. How can I remove a hydrogen to make sure that carbon is positive? Do we know any chemistry that involves alkanes? It begins with R and is not resonance. Is that? No. It's a radical reaction. Yeah, you're responsible for it. Okay. If we go through and run a radical reaction, I should be able to do a substitution, put on the bromine. Okay. How do I do that? We're actually going to bring in a reagent here. Minimally, what do we need? Bromine. We need a radical initiator, so we got a peroxide. But bromine can't just be added as Br. Br2 or HBr are two common issues. If we add HBr, what happens? We add hydrogen as well. We do an addition reaction. What kind of radical reaction do we want to have run? Radical substitution. If we had just added Br2, what would happen? You get an addition reaction again. Two bromines now add across the double bond. Okay. This is kind of cool. I'm starting to see my pieces. So we clean this up a little bit. I now have that piece. The other piece. What do I know about that piece? What charge does that piece need to be? Why does it need to be negative?
Because it's attached to two
attached to more electronegative elements, and if I take a look at the piece that I've already identified, I have a partial positive charge on that carbon. For it to link up to the oxygen had better be negative, otherwise charge repulsion. So let's take a swing at it. I need to bring in a negatively charged oxygen. What else is attached to that negatively charged oxygen? Let's include the other 3 carbons. I've now added a negatively charged reagent. This is a big no-no. When dealing with synthesis, you have to be working with neutral reagents. So how can I make sure that this negatively charged species that I'm adding here maintains that negative charge without showing a negative charge? Make it an ionic bond. Now what happens? Well, the end result, we now have our product. We've done it in 1, 2, 3 steps. Did we have to make that side of the molecule? No, we could have made the other side and worked our way towards it. Okay, but all we're trying to do is find where a pattern breaks and just work with it, see what happens. If you found a different place to break, you may be running a different synthesis. How do you decide which synthesis is better? Lots and lots of time evaluating each of the steps and deciding which one is better. You're not in that situation yet, so what you should do is put a synthesis down, any synthesis. You now have partial credit, move on. If you got time, do the question again and see if you can come up with a different synthesis. If you can come up with a different synthesis, now you can evaluate the 2. Ooh, one of those was better, that's the one I should write as my answer. Questions? How many of you think this is easy? I don't think it's easy. Yeah. Yes, we'll talk about that in just a second, actually. Okay, because we haven't nailed down all of our reagents perfectly. Okay. Other questions? So, what you just mentioned, Terry, was that we had an alternate reaction. Is there another way that I can do that radical substitution? Both of those reagents will do the exact same thing. Is one of them better than the other? And yes, we did talk about this first semester. Those of you who didn't have any first semester, theoretically, they talked about it as well. Let's pretend, say, by accident, we didn't include the ROR. What happens? An addition reaction. So we're now sticking a reagent in there that does an addition reaction and a substitution. What happens to your yield? Drops. Okay, we get a horrible yield. What happens if, say, we forgot the light with NBS? Nothing. Nothing happens. Okay. What does that mean? Not only do we need the light, but our end result, if we add NBS, is only going to be the substitution. Which of those 2 reagents is going to be the better combination? The NBS. This now comes into grading. Okay. Which answer gets the most points? NBS gets the most points, not the BR2. How much of a difference in points is that? Relatively small. Okay. We're looking at half a point at most. Not a big deal. This is where specifying getting something down helps you. If you don't have anything down, you get no points. But if you put down the BR2 and the ROR, it at least works. It just doesn't work very well. NBS works better.
So when would you use BR2 again?
Peroxide, you wouldn't. the better reagent always is the NBS and the light. And the only time you would bring in the Br2 is if you were trying to do the addition reaction, and then you ignore the ROR, the peroxide initiator. Last point that we can mention, you'll notice I did not specify the strong base. What base should we write there? So strong base now gets you partial points, but we need a reagent for that to be accurate. Give me a strong base. Sodium hydroxide. Good. We now have a neutral species being added, which is good, just like we had with the last one, our KOH. So we've got a neutral strong base being added. What's the issue with strong bases? It's also a strong nucleophile. What's our substrate? An electrophile. So if we add sodium hydroxide, are we going to get just the elimination? No. We're also going to get the substitution. So what could we do to change our reagents such that we can ensure that we only get the elimination, or get mostly the elimination? If we switch to a weak base, we're pushing that now into the SN1, E1. Those directly compete with each other. Okay? So we don't want to go to a weak situation. We still want that strong to ensure that we get our product. But now the question is, what other characteristic do we include? And as Terry was suggesting here, we want a bulky base. Why? What happens if it's bulky? It sterically prevents it from acting as a nucleophile, and we can prevent the substitution. What other thing could we add? Helps elimination reactions? Heat. So in a simple three-step reaction, we went through and looked at 1, 2, 3, 4, 5, maybe 6 different conditions to get to a final answer. Okay. It takes practice working through multiple synthesis reactions to pick up those patterns and find the best places to work through it. Do the best you can. Worry about the rest later. Okay. Questions about that? Okay, I'm going to go ahead and erase it all. And I'm going to go through and I'm still going to include this. Say our NBS in light. And we'll do our T-butoxide. Any ideas what we're going to change about this? That is now your only source of carbon. So if we think back to what we did last time, we added our KO, CH2, CH2, CH3. That step is now invalid. Why? I can't bring in those carbons. The only carbons I can bring in have to start at the, 2-bromopropanol, propane. Okay, so that step is now invalid. Okay. On an exam, put it down. You got something, you're at least there, you may have just missed one of those parts. Okay, but you've at least got something to work with. So now the question is, how can we possibly make that reagent? Because we know that reagent works. So this question now becomes a problem within a problem. You have to make that now. It's a second synthesis question. How do we go from our propyl bromide to our active nucleophile? If we add just peroxide, so our peroxides tend to be radical reactions, and those radical reactions initiate what? Substitutions for hydrogens. What are you substituting? Yeah, there's nothing there to substitute. right, let's redraw that last reagent. What does redrawing that help you with? Three carbons, 3 carbons. Okay. We don't even want to look at Grignards yet, because Grignards make carbons negative, and that's officially haven't been talked about yet. We want a negatively charged oxygen out there, and we want it at the terminal position. Can I get an oxygen to the terminal position? What is the reactivity of that blue carbon? In our product, it's positive. In our starting material, neutral. Crap. How can I get chemistry to that carbon?
What about the alkene?
What do you mean, what about the alkene?
You could add water across the carbon.
So if we run our very first step a second time, we now have the alkene. I now have chemistry at both those carbons. I only want chemistry at one of those carbons. How can I get an oxygen to happen only at the terminal atom of our alkene? So as another hint, what we're asking for is this. How do we get that? So we got that, then I can do KOH. Remove that hydrogen, we're there. What reagents can I do in that step? As a hint. What adds hydrogen and OH across an alkene? Our BH3 and THF followed by peroxide. Okay? All of these reactions are things that you know, but by a simple change in our starting only source of carbon, we took something that we had solved in 3 steps, and it now needs arguably 1, 2, 3, 4, 5, 6 steps. Okay? It's the same question being asked each time. Find the patterns. Where do you break bonds? Okay? The bonds that we're trying to break are the most polar ones, which means they're the bonds around our electronegative atoms. So find your electronegative atom, see how that affects the chemistry. See if you're at that point. We look back to our starting material. It's our first carbon that needs to bond around that oxygen. First carbon in our starting material is not reactive. So minimally to go through, I have to get chemistry to that position. I need a new functional group. How can I get chemistry to that position? Well, can't do addition. Can't easily do radicals because that halogen messing with it. Okay. Acid-base doesn't work because it's not a particularly acidic position. Elimination, ooh, that's a possibility. Substitution would only happen where the halogen is. So by looking at where you want to shift that chemistry to, you can now decide what type of reaction to run. Once you know the type of reaction, you can now do reagents. Once you get the reagents, you now have a new problem. Solve the new problem. Very, very slow, very, very methodical. One of the biggest mistakes that I ever made during an OChem test was in a stupid synthesis question. And since I never memorized the reagents, I had to draw out a mechanism all the way through. And I got this nice little note on my exam afterwards, like, this mechanism is pretty nice, but you forgot that carbon, which meant the whole thing was wrong. So when it comes to synthesis, you need to be very careful about counting your carbons and making sure they don't disappear or magically appear. This is where it becomes very important to watch and count atoms. So those of you that hated smart work, I just missed a lone pair. That's the only reason I got the question wrong. I agree with you. That is annoying. But if you scale that into a full-on synthesis problem, missing that lone pair can turn into getting the entire question wrong, which is how SmartWorks grading you. It's getting you to look for each and every single one of those atoms and be very methodical and careful about your problem solving. Questions? Is synthesis on the exam? Absolutely. Is full-on synthesis, here's a starting material, here's a product, give me the synthesis on the exam? Absolutely. 1. Okay. It will also show up in the multiple choice. Here's 3 different possible syntheses. Which of these works? Okay. And it's looking and evaluating each of those changes and say what happens at each stage. Okay. I think the multiple choice are a little bit easier, personally. Okay. It's not that bad, I promise. Ish. Questions? You guys look awfully depressed. Okay. Internal ethers, epoxide synthesis. Okay. We can do a Williamson ether reaction internally. Okay, so if we go back to where we'd ended last week, if we look at a Williamson ether, we're adding our nucleophile, our alkoxide, to our alkyl halide. And they're 2 separate species. Do they have to be 2 separate species? No. It can happen internally. And internally, we would expect something that would form roughly a 5 to 6 membered ring. Why a 5 to 6 membered ring? Those are our most stable. Okay. Which brings up an interesting question about our epoxides. What does an epoxide look like? A 3-membered ring. And our epoxides, it's not a double bond. Our epoxides turn out to actually be relatively stable in the grand scheme of things, which is a bit odd. Okay. So we can actually form these and they aren't too bad. So instead of going through and doing an epoxide formation using our standard reagent, which we talked about from chapter 12, MCPBA, using that kind of weird 5-arrowed mechanism, we can also go through and do it via a Williamson ether process. Okay? And according to the Williamson ether, I need an alkoxide and I need a halide. Okay, so what we're going to do is start with an alkene. That alkene relatively neutral. We could actually be really obnoxious and start with a alkane, giving you a nice step up, giving you an alkene. And I'm also telling you that first step. We're going to add Br2. Predict the product. Come up with that product. Do a new reaction to it. Okay? And see if you can't get to an epoxide. So our end goal in its simplest form would hopefully be something looking like that. Okay? See what you can come up with. I'm not going to give you a whole lot of time with it. Sorry. Kind of nice and kind of mean. Kind of nice because I gave you a first step. We could add bromine. What most people drew me was the dihalide. Good call. Good job. We got a problem with that though. If we have the dihalide and we now need an alkoxide, then one of the next things we would need to do is do a substitution where we trade an OH, might as well just say a negative OH just for the heck of it, for a halogen. Okay. But if we did that, what would we get for our product? 2 OHs. There is no difference between those halogens. Ouch. Because I need a halide and the oxygen. I can't get away with just one. So what we want to do is somehow tweak the reaction such that we don't go all the way to the dihalogen. What could we do? What we could go through and do is change our reagent to, instead of being just Br2, Br2 in the presence of water. Br2 reacts to form the bromonium ion as our intermediate, and as long as water is present, what happens? Water will act as our preferential nucleophile instead of the bromide, and we would end up with the trans addition of our bromine and our OH. We need the alkoxide, which means we need a negatively charged oxygen. How can I get that negatively charged oxygen? I need to add a strong base, and that'll get me to my final product. Is stereochemistry important here? one of those yes and no-ish kind of things. Okay. We would end up with an enantiomeric mixture. So we go all the way through. This would have its enantiomer. Okay. The reason why our stereochemistry becomes important. Let's ignore how we got that material there. Let's just say we started with it. But I'm going to change it further. I'm going to say we started with this. What happens when I add the strong base? Does this elimination or does this substitution reaction occur? No. We're looking at an alkoxide, which means we are looking at a negatively charged oxygen, which means it must do a backside attack on our leaving group position. Where's the backside of that bromine bond? The other side. Can I do this elimination? No. So to go through and do the epoxide according to this synthesis, we have to have the trans alignment of our leaving group and our oxygen. If they are not trans, we don't get the result. Okay? An important note to make when you go through and do it. Questions? So we now have two ways to make epoxides. Whoops, as I walk into the wall. Within that last reaction, what we mentioned is that our epoxide in either synthesis starts with an alkene. The problem with our alkenes is that we can react on top or on above or below our pi bonds. Right? Which means when we go through and do the reaction, there are two products for an epoxidation reaction. Okay? Regardless of which method we use, either MCPBA or going through the Williamson ether. This is a bit obnoxious because we get two products. Right? Is there any way to avoid this? Kind of not really. As far as you're concerned, no, not really. But leave it to an organic chemist to invent a reagent that then prevents one or the other product from forming. Okay, so this is just a side note. Sharpless happens to be a famous organic chemist, created this fancy-dancy little reagent. So plus or minus DET. So DET is just the abbreviation of that compound. When mixed with a titanium structure, and then we try and run our epoxidation reaction, and what ends up happening is we end up getting only one of the epoxide enantiomers over the other, depending on which we started with, plus DET or minus DET. So all it's saying is we can force certain things to happen the way we want to. We just have to be very careful with our reagents, which also boosts the price tag. So we never do those in lab. Okay? In our labs. The next big thing that comes out of our epoxides is how do they end up reacting? Okay, so we can make our epoxides using MCPBA or doing our bromine water and our KOH or some other strong base. Okay, now that we've got the epoxide, what can we do with it? Okay, well, the epoxide's a pretty neat functional group because depending on the conditions, we can change how it opens up. Okay, it is still a stress structure. It does want to break open. Okay, so we either run under basic or neutral conditions or acidic conditions. What's the difference in our products? Let's say we compare this guy under basic condition or neutral or our acidic conditions. What was the difference between those two products? What's that? Yeah. The nucleophile attacks a different carbon of the epoxide. Under basic or acidic conditions, our nucleophile attacked the least substituted carbon. Whereas under acidic conditions, where did our nucleophile attack? The most substituted. Okay? So our epoxide can allow us to get some pretty interesting chemistry coming out of it, depending on what conditions we run under. So this is one of our big things, just like with permanganate. We had to watch our conditions with permanganate. If we were under cold dilute conditions, we just did an addition and we formed a diol. If we were under hot conditions, what happened? You did the oxidative cleavage and you end up fully oxidizing everything. Your epoxides have a similar thing to watch out for. Are we running under basic conditions or acidic conditions? That subtle change changes the dynamics of how the reaction works. Right? So let's look at where that change is most relevant under our acidic conditions. If it's acidic, there is now H plus floating around. That is now the most reactive thing present. That H plus needs to be neutralized. What can it be neutralized by? Lone pairs on our oxygen. Those can react with the H plus, and we end up forming our first intermediate. Does oxygen want to be positively charged? No. So it is now a phenomenal leaving group. Okay, so much so that it's already started to kind of pull itself away from the structure. So that means when we go back to look at our epoxide, are both those bonds identical? No, the oxygen's already starting to pull away from the structure, which means one of those bonds is effectively already broken. So push it to the extreme. If it already breaks, the oxygen takes the electrons, and what charge would be left on the carbon? A positive charge. Where is that positive charge most stable? Where there's more electrons, it's under the more substituted position. So as soon as we've now made that oxygen a great leaving group, our nucleophile is going to come in and attack the most substituted carbon, because that's the most positive carbon. The other one won't be very positive because that bond won't have polarized as much, which means our nucleophile attacks the most substituted position, and we end up with the result we see. When we move to the basic conditions, this one's a little bit of a sort of shorter mechanism. The most reactive thing now is the nucleophile. What charge is the nucleophile? Negative. Okay, so we're going under a strong nucleophile. Where is it going to react? What does the negative need to stabilize? A positive. So we want to find something that's positive. So we can now go to our epoxide and say, where do we have a positive? The bonds within the epoxide have not started to break. The oxygen is a horrible leaving group. Okay. So under those circumstances, both those carbons are equally positive. So where does the nucleophile attack? The least sterically hindered position, because we're saying both those carbons have the same charge. So we can't look to charge being a difference between them. The only thing we can use to look at to tell the difference is sterics. Which of those is least sterically hindered? Which of those is most likely to react with the nucleophile? That ends up being our least substituted position, and our nucleophile attacks the other location. Under both mechanisms, or both types of conditions, what mechanism are we running under? And actually, before we even move into mechanism, I apologize, what type of reaction is occurring in the ring opening step? So we've got our ring open in here, and we've got our ring opening here. What type of reaction occurred? The nucleophile, we can't say added, because under an addition reaction, what are we adding to? The double bond. We don't have a double bond. It's a substitution. Why is that a bit weird? When you ran a substitution reaction, you had the substrate and the nucleophile, and you ended with your product and the leaving group. Start with 2, end with 2. Why is this one weird to classify as a substitution? Your leaving group never left the structure. It left the atom where the chemistry was occurring, but it never leaves the structure. It is still a substitution. When we look at our reaction, what we have to do is focus on where the chemistry occurs. The rest of it is just there to confuse you. So ignore the rest of it. Focus on the atom where the chemistry occurs. Under basic conditions, what happened at that atom? A nucleophile attacked, the leaving group left. Under the other conditions, nucleophile attacked, leaving group left. Identical situations. It's still a substitution reaction. What would the next logical question then be? Which mechanism? What was that, Princess? Why SN2? It all happens at the exact same instant. We never formally form a carbocation, right, in our acidic conditions. All that happens is we polarize that bond. We're still doing a backside attack all the way through it. Okay, so under both conditions, it's still SN2. We just end up seeing some kind of weird oddities within it. Because when you look at the SN1, where would we expect our nucleophile to have attacked? Our most substituted position. Where did our nucleophile attack in the epoxide opening? Under acidic conditions, went under the most substituted. So we'd kind of lean towards SN1. So when we're looking at the epoxidation ring opening, it's kind of like an SN1.5. Okay? Not everything comes out perfectly. Questions? The next thing, just because everybody seems depressed on this, nobody sat down and just said, oh, this is the answer. They went into the lab, they tested it, like we did with the Diels-Alder reaction. They tested it, saw what happened, said, oh, crap, we've got something that's halfway in between. Right? No one sat down and said, we're going to screw these guys over. Okay? These were all things that were done over probably the last 100 years. So, what is or are the products? Notice I did some tweaks here. We went to Cl2 as opposed to Br2. Still works, same general idea, but everybody panics because it's now not Br2. We still form that chloronium ion, that sort of cyclopropyl intermediate. Does chlorine want to be positive? No. It wants to steal the electrons, which means that chlorine right now is a really, really good leaving group, which means I can now bring in a nucleophile such as water, and that water will now attack which position? The most substituted, because chlorine's a good leaving group. Okay? Same thing as just happened with the epoxide, exact same thing. The more stable our leaving group, the more likely our nucleophile attacks the most substituted position. Our first product. We then follow this up with NaOH. What happens when we add NaOH? We form the epoxide. We then follow this up with the next reagent, which is going to cause the ring opening. And now becomes the question, what's the nucleophilic atom in our ring opening? Which OH? CH3OH. Okay, the one on top. Good call. Why the one on top? Not a bad guess. We'll come up with better reasons for why the top one is our nucleophile. Most commonly, your nucleophile is on top. Okay, so we're going to end up with two oxygens coming off here. One will be our original oxygen from the epoxide. The other one will be the oxygen from our nucleophile. Which one's which?
The one on the left is the
Sorry, I gotta think, make sure I got that right. Yes. Why? If it's basic conditions, our nucleophile should have attacked the least substituted position. So it's not basic conditions. Where are those conditions specified? TSOH, which happens to be straight from that lecture that you all watched, toluene sulfonic acid. It's an acid catalyst. That acid catalyst protonates the epoxide first. This then forces our ring opening to happen where we put our nucleophile at the most substituted position. Okay. Your conditions may not be obvious and you may see things stashed as TSOH. Very, very common acid catalyst. How many remember seeing the part of the video where it said anything about TS? 2 or 3 of you. Good. The rest of you should go watch the video again. Okay. Which isn't a problem necessarily. Just realize the test is Wednesday. Okay? Questions on that? Did anybody have a slightly different answer? Say like with one that involves stereochemistry? Yeah, you're going to have lots of different stereochemistries here, which is why I didn't specify it. So on a multiple choice test, how would you know whether you should worry about the stereochemistry? If it's shown. If they don't show it, don't worry about it. If it's just asking for a general synthesis, predict the product, stick with this. If you got time, go back and work on it. So what happens if we go back and work on it? I really only care about stereochemistry up to this point. Why do I not care before that? The intermediate steps aren't going to result in anything different. They're going to get us both to the epoxide with its enantiomer. When we go through and then do the reaction, what is the orientation? Say it's pick one. If that is wedged, what does that tell me happens to the methyl? That methyl must be dashed. What does that tell me must happen to the OH? Why must it be dashed? It's a backside attack. Still an SN2 mechanism. The other product? Or we could write plus an enantiomer. Questions? Yes?
On the step where you're adding the sodium hydroxide there,
Yeah.
and then you're forming the epoxides,
Yep.
so could the sodium hydroxide or the physical hydroxide could take the hydrogen that's connected to that carbon with the chlorine?
Is that a possible result? Yes. Trying to do an elimination. So let me mark that. You're saying something like this? Take that hydrogen?
No, the hydrogen was connected to the carbon with chlorine, which is deprotonate that carbon,
Okay.
which would then also give it.
Then where would that negative charge go? Okay. Which is why I pointed out the hydrogen that I did, because if we pull that hydrogen off, we get a negative charge here. What could that negative charge then do? Could do an elimination. But the question I would first ask before we have initiated really much of that would be, you're having the base pull a hydrogen from what? Where did that hydrogen come from that you just mentioned?
Well, what I was talking about, which was incorrect, that was on that carbon.
So you're saying the base would pull a hydrogen from carbon before it pulls the hydrogen from an oxygen?
I just wasn't sure because that chlorine, I wasn't sure if the chlorine connected to it was going to be pulling.
Interesting question on ranking acids and bases, so I'm going to have to clear everything there. Pull this up. When we look at ranking acid and base strength,
Yes, our inductive effect.
was kind of horribly written. You need to go through and follow your rules, starting with what? Charge. So once we remove the hydrogen, we'd have the same charge all the way across. Then what did we move to? Size. Then electronegativity. Then you can move to resonance. And then you can move to induction. Those last two are both molecule effects. These two are atom effects, or really the top three are atom effects. Okay. So if we go back to that previous question, you were talking about removing a hydrogen from carbon versus a hydrogen from oxygen. Which hydrogen is more acidic? Because more electronegative. It's not bigger. Within a row, they're ultimately the same size. Okay. What happens if we now switch this up to an amine? Okay. So if we look at trying to do a substitution reaction with an amine, NH3 as opposed to water, we might predict that we can go through and just do our substitution. The nitrogen is a better nucleophile than oxygen. Why is it a better nucleophile? Nitrogen is lower in electronegativity than oxygen, meaning it is more willing to share its electrons. So nitrogen being the better nucleophile, we would expect to react similarly to our oxygen, and we could form our primary amine. We've just put on the carbon. Turns out that when we mix our ammonia with an alkyl halide, we don't end up with just the primary amine. We end up with the secondary amine, the tertiary amine, and the quaternary amine. We get the whole freaking mess. Okay? And one of our primary reasons being is because the nitrogen is such a good nucleophile. Okay? As soon as we put on one alkyl group, we still have a lone pair on that nitrogen. That lone pair is still a good nucleophile, so it continues to react. Okay? So when we're looking at substitution reactions with amines, they're horrible. Okay? We very rarely use them because we can't control very well the efficiency of producing a single product. We get a whole bunch of them. But if we push this a step further, okay, is it possible that we could make just one of those products? And how could I make just one of those products? As a hint, that one product that we can make with relatively good efficiency is the quaternary ammonium ion. How can I ensure that I get almost everything as the quaternary ammonium?
Your start material is the tertiary?
Nope. Still start with the primary amine. Add an excess of the alkyl halide. Okay, that's the scientific term. The non-scientific term, add a crep load. We add a ton of that alkyl halide. That's now going to put that alkyl halide, or the alkyl portion, on every single one of those available nitrogen lone pairs, and we can end up with a quaternary salt. Okay. Pretty synthetically useless because at that point we've now completely removed the reactivity of the nitrogen, and we're looking at, for all intents and purposes, an alkane. Okay. Until a very special someone came along, looked at that, and said, actually, nitrogen does not want to be positive. It wants to steal electrons. And if it wants to steal electrons away from one of the carbons, that nitrogen can act as a leaving group. Okay. And if I go through and add a base to it, and a little bit of heat, now I don't run the substitution, I run the elimination reaction. Okay. This is the special characteristics of our nitrogen. Yes, it's fantastic, we can do these substitution reactions, but it's so sporadic in its reactivity, it's not very helpful for us. So what we can do is add a crap ton of our alkyl halide, push us all the way to the ammonium ion. Once we're at the ammonium, I can now add a whole bunch of base and heat, and I can now push the elimination. You'll notice that if this is the reaction we're going to run, we are very particular with the type of halide or alkyl halide we add. We add a methyl halide and not, say, an ethyl, okay, or a propyl, or anything longer. Why do we stick to the methyl? Can I eliminate from a methyl? If nitrogen took the electrons away from one of those methyls, can I form an alkene? No, there's only one carbon. That's why we stick with the methyl halide. That methyl halide now converts our nitrogen into a phenomenal leaving group so that it can take electrons. What do we then need to find? Hydrogens on a nearby atom. In particular, we could reference it as an alpha carbon. Okay? And we could take those electrons and we could go through to form our double bond. You'll notice that what I just drew on there was enough arrows to produce two products, which means there are two possible products in this elimination reaction. Why did the book only show one? What's that? The one they showed was the major product, and that's the one we get exclusively. We don't get the one in blue. It's a bit weird, because when we look at those two products, which product would you expect, based on first semester knowledge, should be your final product? The blue one, because it's the Zaitsev product. It's our most substituted double bond. That is the one we should get as the product, and that is the one we do not get as a product under these conditions. It makes no sense, and because it makes no sense, the person that discovered this gets to attach their name to this type of product. And it becomes known as the Hoffman product, or our Hoffman elimination reaction. Okay. That reaction has to do with looking at the Newman projections of the transition state. So what we're talking about is doing the elimination from carbon 1 or carbon 3. I was going to have you guys draw these out, but instead we'll just use what the textbook gave you. When we go through and do those eliminations and look at that Newman projection, to get the proper projection down the 2,3 bond, which means we'd be forming our alkene in our most substituted position, we'd have our alkyl chain and the leaving group butting up against each other. This drawing, they didn't show it good, is known as what type of Newman projection? There it is. It is a Gauss-Newman projection. Is that the lowest energy projection? No, which means not particularly likely to form. If we look at the elimination reaction in the other alignment, what do we notice? Not even really anti. I mean, it's a lower energy eclipsed form. Which transition state is more likely to form? The eclipsed one or the Gauss one? Eclipsed. Well, if that one forms, where's our elimination most likely to occur from? The one that forms, and we end up forming our double bond at the terminal position, or our least sterically hindered product. This slide is quite literally straight out of the textbook. Okay? So, when you're seeing amines and you're thinking elimination, draw your elimination products. Okay? And if there's multiple places to do your elimination, draw them all. And then decide what is the difference between those. And it's ultimately going to have to come down to the thing that you added to it, the thing that changed. In this case, it is the formation of that double bond. Evaluate it. Is it the most stable or least stable? If it's the most stable, you better be saying that your conditions are Zaitsev. If it's the least stable, you'd better be saying your conditions are for the Hoffman elimination. How do you know you have Hoffman? You see that nitrogen floating in there? You're probably looking at a Hoffman. All right? Questions? I fully expect to not cover all the material, but I do want to get a little bit further here. What is the reactivity in a CH group? Nothing. But if we now string that CH group near another functional group, we can change its chemistry. So we can bring in a carbonyl, and we may say, well, the carbonyl has chemistry. It does. But those hydrogens are now also reactive. Those hydrogens are reactive because if I remove one, I would have H plus and C minus. Well, would I ever expect to remove a hydrogen from carbon? Jimmy was just asking earlier. We looked at that, we say, oh, that was a horrible idea. We all made fun of Jimmy. I apologize, Jimmy. We didn't mean to make fun of you. Okay? That's a bad idea. And yet, 2 slides later, what am I doing? I'm doing the exact same thing. Why is it okay under these circumstances to remove that hydrogen? This is resonance stabilized. And I'm not really looking at a negative charge on carbon. I'm looking at a negative charge on oxygen. Can oxygen hold a negative charge? Yes. That resonance stabilization is one of the reasons why we can pull that hydrogen off. Okay. What we are looking at here is the keto-enol tautomerization. And when we talked about the keto-enol tautomerization, we just kind of said which one was favored. Left or right? For those of you screaming right, it's the left one. The left one is favored. All of the reasons and explanations on that go into bond energies and bond calculations. You are more than welcome to take a look at your textbook because it does a reasonable job talking about it in one of our earlier chapters. Okay. Ultimately, all you need to remember, carbon-oxygen double bond should stay. But when we remove that hydrogen, what does that now trigger? A negatively charged carbon. What can we do with a negatively charged anything? React it as a nucleophile. So the rest of the chapter is now looking at that nucleophilic character of that carbon. Okay. So, to make it happen, what do we have to do? Remove the hydrogen. Okay. Again, I was going to have you guys go through and do a mechanism. Kind of low on time here. But what we would end up with is that as our product. And this one is a product. Which one was more acidic? Left or right? Why is the left one more acidic than the right one? There's more resonance in the left one than in the right one. Those of you think, oh man, that was really hard. We shouldn't have done that in second semester. You're right, we shouldn't have done it in second semester. We did it in first semester. We actually already talked about this reaction. Okay. We can use resonance. We could also pull at pKa's. The pKa's of the one on the left is 9. The pKa's on the one on the right, roughly 17. Okay. What is the pKa for water? 16. So the hydrogen next to a carbonyl is actually pretty darn close to the same acidity as water. Okay. It's pretty impressive how much that resonance effect contributes. Right? I swear this is the last slide and I'll stop talking after this. There are a variety of bases that we can go through and use. Which base do we want to use? Well, it depends on what we're trying to do. Okay? If I want only the nucleophilic carbon, I'm going to be very careful with the choice of my base. Because if I use just a standard ethoxide, sodium hydroxide, how much of the nucleophilic carbon do I make? How are you already saying not much? Look at the arrow. That arrow says that most of our reaction favors the left. If I want a lot of that nucleophilic carbon, I can switch to, say, hydride or nitride. What is special about the hydride or nitride in comparison to the oxide? difference in electronegativity, and case of the hydride, difference in size. Which of those three bases is the most basic? The hydride. It is the smallest and least electronegative. Okay? Very important distinctions to go through and make when you're evaluating those. And I will